Okay. I think recording শুরু হয়েছে. Okay. So now we're going to start from where we ended last class. So last class একটু lecture note part বাকি ছিল, একটু ছোট একটা portion. You can hear me, right? সবাই?
হ্যাঁ আপু, শোনা যাচ্ছে।
So আমরা হচ্ছে লাস্ট ক্লাসে যেটা শেষ করছিলাম সেটা হচ্ছে যে ট্র্যাপ সারফেসেস এর জেনারেলাইজড একটা condition আমরা figure out করছিলাম for the apparent horizon, and then the generalized condition for the apparent horizon looked like the following, where we had the gradient to be 0, right? And that is what gave us an idea of where the apparent horizon is placed, right, for the particular geodesy. Now, if we apply this to the Schwarzschild and also the Reisen-Nordström solution, in that case, we see that it coincides exactly with this condition, which gives us the event horizons, right? So therefore, like I said, these are, all of your trap surfaces, and these are your black holes, which coincide with the conditions for black holes and so on. So apparent horizons are more or less a generalized idea of black holes, not necessarily with a singularity. Okay. So now moving on from here, we're going to focus on the area law theorem. And this is basically a foreshadowing of what we're going to do today, which is, try to understand black hole mechanics, where one of the black hole laws of, well, you can say them, you can sort of denote them as laws of thermodynamics, but typically for black holes, we don't call them laws because, thermodynamic laws are set on stone, something like that, right? But black hole laws are not set on stone. So therefore, most people call them theorems. But since we have an analogy with thermodynamics in general, so we call them black hole laws of thermodynamics. But you will see that what we are going to do now, which is the area law theorem, it will sort of coincide and foreshadow what we're going to do next. Okay, so what is this area law theorem? So essentially, it states that under general conditions, meaning the absence of a naked singularity, and of course, also the weak energy condition, it is testament that the cross-sectional area of the future event horizon, which is basically the event horizon that we denote in general, right? Will always abide by this notion where delta A is always positive or equal to 0, meaning that the area never decreases with time. Okay. Now, this idea is basically based on the fact that we have something called the focusing theorem. Now, we don't need to go in depth on what the focusing theorem really is, but we can understand what it is from a very general idea, in the sense that if you have, let's say, a sort of decomposition of space-time, যেটা আমরা normally call of hyperspaces, like this, right? So you have hyperspaces stacked on to one and another, right? And if you want to represent, let's say, gravitational collapse, right, for black holes per se, so physically gravitational collapse যদি আমরা represent করতে চাই, so তুমি জিনিসটাকে visually এভাবে চিন্তা করতে পারো যে your space time will start to contract, right? Because gravitational collapse যখন হয়, সেই particular space timeটাকে যদি আমি decompose করি, সেই ক্ষেত্রে you will see that the space-time will start contracting to a singularity, right? That is what happens when we have the formation of a black hole. So in that case, let's say as you move through time, so this is increasing time, In that case, you will see that the space-time, but space-like hypersurfaces, যেটা আমরা বলি normally, যে hypersurfaces গুলো are, denoting space. In that case, space gets smaller and smaller and starts contracting, right? So this is an idea of what the focusing theorem means. যে basically, when you draw geodesics like this, and if there is a particular point in the gravitational collapse where you have, the space contracting to a singularity, the geodesics will be left incomplete. Okay, so they will go and inevitably hit the singularity. So this is the basic idea of the focusing theorem. So essentially, a focusing theorem and ideology যদি আমরা consider করি, then of course I understand that if I were to, let's say, draw a sort of, কি বলবো, let's say I want to sort of understand how the geodesics form. Okay, in that case, the focusing theorem tells us that d squared a to the power of half by d lambda squared will always be, sorry, negative or equal to 0. So let's try to understand what this implies. So first of all, lambda over here is the affine parameter. So that means that essentially হচ্ছে আমি একটা জিওডেসিকের জন্য sort of একটা measure করতেছি in regards to the affine parameter, where I'm saying that, I'm assuming that area সাথে সাথে along the affine parameter, how does the, null geodesic really move? Okay, so this is my picture. So now if I have a second derivative like this, which is negative or equal to 0, it implies that I have a particular maximum, right? Because second derivative যদি negative হয়, then you have a maximum. And of course, if the second derivative is 0, it's an undefined point, which then should give you a critical point if the first derivative is 0, right? So essentially, by this inequality, you can understand that we have a particular maximum present. So this implies that if I have the second derivative to be negative, okay, this is one point. And also, if I have the first derivative to be also negative, right? And this is at some point lambda naught. This would imply that if there is given a point lambda 1, which is greater than lambda naught, there should exist some place where the area at lambda 1 should be 0, right? Which means that, let's say, lambda naught is the affine parameter, right? Let's consider or relate it to the time, okay? Because time is an affine parameter physically. So in that case, আমার যদি actually একটা decreasing second derivative থাকে, তার মানে একটা পয়েন্টে আমি যদি কনসিডার করি that dA by d lambda is negative, তার মানে the change in A with respect to lambda is negative, তার মানে হচ্ছে at some point at lambda 1 it will hit 0, and which is something that we imply by this condition as well, right? So তার মানে একটা জায়গায় আমার এরকম একটা পজিশন থাকতে হবে যেখানে আমার এটা 0 হয়, বাট এখানে একটা প্রবলেম আছে, সেটা হচ্ছে এটা যদি 0 হয়, সেই ক্ষেত্রে মানে I should imply this condition that if I have a maximum something like this and একটা পয়েন্টে যদি এটা 0 হিট করে, তার মানে it should be true that this part of the curve is possible, right? But try to think of it from the context of black holes, right? If you write the geodesics and this is the trajectory of the geodesic per se, and it hits a minima at some point, it should be able to come back, right? And by implying the fact that this is negative, this would mean that the gradient is negative, right? Because the first derivative gives you a negative. And gradient negative মানে হচ্ছে যে a partটা is possible if you have a maxima, which is this condition, right? So let me repeat myself. যে আমার যদি এই condition exist করে, which is given by the focusing theorem. So I know this exists, okay? And if I consider that around the maxima, I can have 2 points of the gradient where I can have this portion where you have, the increasing function, right? The increasing function means you have the gradient to be positive. And in that case, it hits the maxima and then it comes down, right? And this is the point where you have the decreasing function and it, has a negative gradient and therefore this is negative. So that means that this point is given by the condition where you have the gradient to be negative. So if this is possible, in that case, it would mean that the geodesics would go hit the maxima, which exists in this point in the focusing theorem ideology, right? Which is essentially the singularity. The null geodesics should be able to come back. But that is not true, right? Because we understand that for black holes, you can hit the singularity and that is it. The null geodesics are then incomplete. So therefore, it must be true that only this part exists. And hence, I should write that this is true, right? So in other words, that I can say that this area of the future event horizon never decreases, which means that it is always ever increasing with respect to your null geodesic, or essentially the black hole event horizon area will always increase, abiding by this particular condition. Okay, so I can write it in words where I can say that the area, give me a second, 2 seconds. Okay, so like I was saying, the area of the future event horizon never decreases. And this is the area law theorem for black holes. Okay, and we will see that this is also a correspondence to the second law of thermodynamics, where you have a sort of analogy with the area and entropy, okay, which we will do now. So starting black hole thermodynamics, where we will basically brief over a couple of laws which are classical. But we will see that to actually make a particular relationship between thermodynamic laws and black hole thermodynamic laws, you actually need a quantum relationship. মানে হচ্ছে মানে proper একটা relationship বা proper analogy বানানোর জন্য আমাদের quantum analogy of black holes দরকার. But now let's just move on to understanding what these black hole laws are. Okay. So first of all, I would like to state that the black hole thermodynamic laws are not laws. Okay. So when I say laws, or in general, whenever we have laws in physics, they're essentially, statements that are universally true, right? And laws are actually interesting part হচ্ছে they abide by universality, right? Which means that in any condition and for all conditions, they stay true. However, black holes that are these laws that we state, they are not entirely set on stone. In fact, because we cannot probe black hole physics experimentally, we don't know for sure if they're set on stone or universal per se. Okay. However, it is interesting to study them with the analogy of typical thermodynamic laws, because we see that there is actually a relationship, and this relationship is more apparent when you have quantum nature of black holes, because we see then that we have things like Hawking radiation, where you can make a relationship with the Hawking temperature and so on, and relate the Hawking effect with thermodynamics in general. তখন গিয়ে দেখি যে আচ্ছা আসলেও laws গুলো have a very ideal analogy with thermodynamic laws. So first of all, we're going to state the laws that we have in general for thermodynamics classically, which are first the zeroth law, right? Where for thermodynamics or classical thermodynamics, zeroth law states that we have a particular constant in nature, which is the temperature, right? And the temperature is constant when it is in equilibrium. So if you have two thermodynamic bodies and they have, opposing or different temperatures, if they are in thermal contact, they will start to, connect in heat, and therefore they will come to an equilibrium temperature, which is constant for both of the bodies, right? So that is zeroth law. And there is a particular analogy, or basically I would say there is an analogous quantity for temperature in the black hole idea, which is basically true for stationary black holes, and that is called the killing field. Okay, and in fact, through the killing field, we will see that the surface gravity actually works as this analogous quantity for the zeroth law. So for the zeroth law in classical thermodynamics, we have a constant quantity, which is the temperature. For black holes, we will see that there is an analogous relationship with the surface gravity. Okay. Now, how do we actually configure the surface gravity? If you remember, we configured it from the killing fields, but the killing vectors, right? Where if we denote the killing vector, G,
What the question আছে এটা
বল,
সারফেস গ্র্যাভিটি কেন অন্য কোনো কোয়ান্টিটি না কেন
শুনি না, একটা আবার বলো। তোমার মাইকটা
মানে আমার
মাফেল।
মাইকে বেশি হলো না আমার আমার গলার অবস্থা খারাপ বেশি আচ্ছা
হ্যাঁ, বলো।
তো বেসিক্যালি মানে আমরা টেম্পারেচারের সাথে করেসপন্ডেন্স এটা ক্রিয়েট করার ট্রাই করতেছি with respect to like surface gravity. Surface gravity কেন অন্য কোনো কোয়ান্টিটি না কেন?
তোমার কথা একটু মাফল হয়েছে, বাট হোয়াট আই আন্ডারস্টুড ইজ সারফেস গ্র্যাভিটি কেন টেম্পারেচারের অ্যানালগাস, অন্য কোয়ান্টিটি না কেন, রাইট? সো এটার কারণটা বুঝবা, সেটা হচ্ছে যে টেম্পারেচারের মানে জিরোথ ল অনুযায়ী টেম্পারেচারের ইন্টারেস্টিং কোয়ালিটিটা কি, যে ইট ইজ কনস্ট্যান্ট, right, at a particular thermal contact, but thermal, let's say, okay, so if you want to visualize the zeroth law, so you have, let's say, two bodies, right? And let's say this is body A, this is body B, this is at some temperature Ti, this is at some temperature T2, right? Once you connect them through thermal contact, তার মানে কোনো ধরনের হিট ট্রান্সফার বা টেম্পারেচার ট্রান্সফার বা সামথিং অর দি আদার ইজ পসিবল অ্যামং দ্য টু বডিজ। যখনই এটা তুমি পসিবল করে দাও থ্রু সাম মেমব্রেন, রাইট, তখনই কিন্তু দে উইল স্টার্ট টু কাম ইনটু ইকুইলিব্রিয়াম, থার্মাল ইকুইলিব্রিয়াম যেটা আমরা বলি। তো তখন হচ্ছে দে শেয়ার দ্য সেম টেম্পারেচার উইচ ইজ কনস্ট্যান্ট অ্যামং বোথ অফ দ্য বডিজ। ওকে, সো এই যে টেম্পারেচারটা এক্সিস্ট করতেছে বিকজ অফ দিস মেমব্রেনের থ্রুতে হিট ট্রান্সফার, এই টিপিক্যাল একটা রিলেশনশিপ আমি ব্ল্যাক হোলস এর জন্য বিল্ড করতে পারবো, যেটা আমি এখন দেখাবো। ওকে, এন্ড উই নো।
আচ্ছা তো আরেকটা কোয়েশ্চেন সেটা হচ্ছে যদি দুটো ব্ল্যাক হোল মার্চ করে তখন কি তাহলে এই টেম্পারেচারের মধ্যে সারফেস গ্র্যাভিটি কনস্ট্যান্ট থাকবে এরকম কিছু?
না, আমি ব্ল্যাক হোল মার্জারের কথা বলতেছি না এখন। আই এম জাস্ট টকিং অ্যাবাউট আ স্টেশনারি ব্ল্যাক হোল ইন জেনারেল। ওকে, সো লেট মি লাইক ব্রিফ ফার্দার এন্ড ইউ উইল আন্ডারস্ট্যান্ড হোয়াট আই মিন। সো লাইক আই ওয়াজ সেইং দ্যাট আমরা প্রথমে হচ্ছে সারফেস গ্র্যাভিটি কিভাবে মডেল করি, উই হ্যাভ দ্য কিলিং ফিল্ডস, রাইট, দ্য কিলিং ভেক্টরস, এন্ড উই কিলিং ভেক্টরস দিয়ে কিন্তু আমরা হচ্ছে আমাদের কিলিং হরাইজনটাকেও ডিফাইন করতে পারি, রাইট? যে আমরা জানি যে কিলিং ফিল্ড যেখানে জিরো হয়ে যায়, রাইট, নাল হয়ে যায়, বা কিলিং ফিল্ডের নর্ম যেখানে নাল হয়ে যায়, সেখানে হচ্ছে আমরা কিলিং হরাইজনটাকে ডিফাইন করি, উইচ ইন পার্টিকুলার ফর ব্ল্যাক হোলস ইজ দি ইভেন্ট হরাইজন। সো সেখানে হচ্ছে কিলিং ফিল্ড গুলোর নর্ম জিরো হয়ে যাচ্ছে। সো ইন দিস রিলেশনশিপ উই ক্যান অ্যাকচুয়ালি ফিগার আউট দি সারফেস গ্র্যাভিটি in terms of the killing fields, which is which we denote as kappa, and we can define the relationship via the norm of the killing field. So, and this is a general comparison. This will work for all surface gravities. Either this is, a Risen-Nordstrom black hole or a Kerr black hole or a Schwarzschild black hole or so on. But you have to remember that this has to be true for stationary black holes. তার মানে যে ব্ল্যাক হোলগুলোর স্টেশনারি সিমেট্রি আছে, that means that symmetric in time, or basically the metric is independent of time, সেগুলোর জন্য this is true. Okay, so I know I can derive the surface gravity, and in fact, if you now take the sort of derivative in terms of the killing field of this surface gravity, you will see that the surface gravity is constant along the killing field. So in principle, it means that this kappa basically does not change when you have the surface gravity measured in the event horizon. Okay, so what I mean by that is, if let's say your killing field, or let's say the norm of the killing field, and by killing field I mean the killing vectors, right? Because of course they provide you with a field and you can get their eigenvalues and so on. So if your norm of the killing field,
এই কিলিং ফিল্ডটা কি আমাদের গ্র্যাভিটেশনাল ফিল্ড?
না, killing fieldটা হচ্ছে বেসিক্যালি তোমার, well, okay, so তোমার killing vector আছে না?
হ্যাঁ, মানে দ্যাটস হোয়ার দ্য কিলিং ভেক্টরস লিভ। সো
হ্যাঁ,
ইজ ইট দ্য সেম
it's-
অ্যাজ আওয়ার গ্র্যাভিটেশনাল ফিল্ড অফ দ্য ব্ল্যাক হোল?
না, not necessarily. Gravitational field এর excitation কি? Gravitational field এর excitation should be the
গ্র্যাভিটনস।
right, but killing field এর excitation তো graviton না। তো আমি কেন বলবো যে
আচ্ছা,
killing field is the gravitational field and so on?
দে
It's
হ্যাভ
just
পার্টিকলস when they excite, কিলন্স।
না, মানে আমি এই ফিল্ডটাকে আমি একটা ফিজিক্যাল ফিল্ড বলে আমি ডিনোট করতে পারবো না। এসেনশিয়ালি কিলিং ফিল্ডস আর you can think of them as having degrees of freedom, right? So you can sort of map them on a manifold per se, right? So it's sort of like mapping them on some space, যেটাকে আমি একটা field space বলতেছি, but they're not physical. Do you understand? It's not like their excitations will give me particles in general. Do you understand?
Yeah, it's kind of like how we express a vector field.
Yeah, exactly. It exactly is a vector field. That's it. Okay. So এই জন্য আমি বললাম যে killing vectors আর associated field গুলোকে আমরা killing field বলতেছি. That's it. So like I was saying, that if your norm of the killing field is 0 at the event horizon, সেই ক্ষেত্রে আমি সবচেয়ে generalized একটা surface gravity যদি নেই, which is, let's say, for the Kerr-Neumann black holes, and this is general, আমি কেন বলতেছি কারণ it consists of all possible attributes of the black hole, right? Meaning you can have, like the Schwarzschild, just mass, you can have charge, you can have angular momentum. So Kerr-Neumann black hole যদি আমি kappa compute করি using this expression, okay, in that case you will see that the kappa is the following. আমি এটার explicit derivation দেখাচ্ছি না because it's not important, because we did not cover Kerr-Neumann black holes, but you can take this for granted. And this is the formulation of the surface gravity for a Kerr-Neumann black hole. Okay. And you will see that this kappa is constant on the event horizon, because I know for a fact that the event horizon is the killing horizon for us, right? For black holes, sorry, not for us, for black holes. So in that case, if it is constant on the event horizon, it sort of acts like this analog of temperature, because now you have, let's say, two particular spaces, space A and space B, where this particular point in your middle of two spaces is acting as the thermal contact part, and এই জায়গাটাতে তোমার kappa হচ্ছে constant. Okay, so তার মানে হচ্ছে the bridge between these two spaces, you have a constant analogous quantity, which is the surface gravity. So এটা sort of analog আমরা বের করতে পারবো with temperature. I know it is not exactly physical per se যে আমি temperature এর সাথে কিভাবে আমি kappa relationship করতেছি, because there is a lot of things involved over here, especially dimensions. যে টেম্পারেচারের সাথে সারফেস গ্র্যাভিটি ডাইমেনশনস কিভাবে ম্যাচ করে, বাট ইট ইজ অ্যানালগাস ইন দ্য ফ্যাক্ট দ্যাট ইউ ক্যান মেক আ সার্টেন অ্যানালজি ইন দিস ওয়ে, যে টেম্পারেচার যেভাবে থার্মাল কন্ট্যাক্ট বা থার্মাল ইকুইলিব্রিয়ামে কনস্ট্যান্ট হয়ে যায়, যেই জায়গাটা আমার ব্ল্যাক হোল স্পেসেস এর জন্য ইকুইলিব্রিয়াম, উইচ ইজ দি ইভেন্ট হরাইজন, সেখানে আই হ্যাভ আ অ্যানালগাস কোয়ান্টিটি দ্যাট ইজ অলসো কনস্ট্যান্ট. So therefore I can make this relationship. And furthermore, you will see that this is true because at the event horizon, I do have a constant temperature, which is T equals to 0 if I include quantum effects, if I include even, Hawking effect and so on. And I also showed you this in the problem set. When you take kappa to 0, you have T to go to 0 as well, right? So এটার ক্ষেত্রে হচ্ছে এই রিলেশনশিপটা কাপার সাথে you can make with temperature, which tells you that there is in particular a zeroth law related to black holes, which is in regards to the surface gravity. Okay. So now this is constant on the event horizon. And so this should be analogous to the zeroth law. We will see in a bit that you can make dimensional analysis to match, but later on, okay? Now, I can state the zeroth law for black holes. So the zeroth law for, let's say, zeroth law of black hole thermodynamics is therefore stated as for a stationary black hole, the surface gravity kappa is constant on the horizon. Okay. Now, we have made so far two analogous relationships. একটা হচ্ছে এই যে এরিয়া ল থিওরাম এর সাথে, and একটা হচ্ছে এই যে জিরোথ ল এর সাথে, যেখানে আমরা কাপাকে ডিনোট করছি উইথ সারফেস গ্র্যাভিটি, অ্যানালগাস রিলেশনশিপ বিল্ড করছি, and এরিয়ার এন্ট্রপির সাথে একটা অ্যানালগাস রিলেশনশিপ বের করছি. সো তার মানে হচ্ছে টেকনিক্যালি নাও ইউ হ্যাভ আ রিলেশনশিপ দ্য জিরোথ ল and you have a relationship with the second law of thermodynamics, right? A similar analogy হচ্ছে, now we question if you can actually state the first law for black hole thermodynamics to be analogous to the first law of thermodynamics in general. So in that case, it was proven in many papers, especially যে বারদিনের একটা পেপার সাইট করছে in the book, you will see. সেখানে proven হয়েছে যে for two nearby stationary black holes, they must be related according to this relationship, where you have c squared delta m equals to c squared by 8 pi g kappa delta a plus omega h delta j plus phi h delta q, where this phi h denotes the electrostatic potential. Okay, so this is the relationship for two stationary black holes that are nearby. And basically, this is how they will influence each other. Okay, so for two stationary black holes that are nearby. Okay, so now you see that there is a clear similarity to how we state the first law of thermodynamics, where the first law of thermodynamics looks like the following, where you have delta E equals to T delta S minus P delta V plus mu delta N, right? যেখানে এই মিউটা হচ্ছে basically chemical potential যেটা সেটা। So you see, it is very similar to how the black hole relationships work for stationary black holes. So therefore, you can sort of make a very heuristic analogy here. You can extend this analogy and say that there is a relationship between, delta S and delta A over here, because I'm already এটা দেখাইছি, just similar to the idea that for the second law of thermodynamics, you have entropy to always increase. আমাদের black hole horizon এর ক্ষেত্রেও we have the area to always increase, right? So you can make a relationship with delta A and delta S like this. And of course, এখানে একটা interesting part হচ্ছে, you see delta A এর সামনে you have the surface gravity kappa, and এখানে we have temperature, যেটা আমরা মাত্র relate করলাম with the zeroth law, right? And এখানে হচ্ছে you have delta V, delta J, okay, horizon, and you have delta phi, phi H, and mu, where a phi H is the electrostatic potential, and এখানে mu is the chemical potential. Okay, so you can see that there is a visible sort of analogy that is possible, right? However, the problem here is that the analogy you can make is formal. Okay, and formal বলতে আমরা যেটা বুঝেছি সেটা হচ্ছে আমরা যেটা একটা ম্যাথমেটিক্যাল অ্যানালজি হয়তো বানাইতে পারবো, বাট আদৌ এটা কি ফিজিক্যাল কিনা সেটা আমাদের বুঝতে হবে, right? So over here I would like to say another thing, সেটা হচ্ছে যে এই phi h টা যেটা সেটা হচ্ছে constant at the event horizon, similar to the angular velocity, which is given as omega h. Okay, so over here আমরা অ্যানালজিটা আমরা এক্সটেন্ড করতে পারবো যে ফার্স্ট ল এর সাথে একটা সিমিলার অ্যানালজি এক্সিস্ট করতেছে, রাইট? বাট we cannot establish it until we can actually match the dimensions. Okay, আমরা দেখতেছি যে একটা ভালো রিলেশনশিপ বিল্ড হচ্ছে, but we don't know if the dimensions is correct, of course, because delta A এর সাথে delta S এর dimensions definitely match করবে না, because entropy আর area dimensions are different. So in that case, let's just hold that for a bit and go to the next thought, যে যদি আমরা zeroth law, first law and second law analogy বের করতে পারি, then of course it should be true that we can extend the analogy to the third law of thermodynamics, right? Now এখানে সমস্যাটা হচ্ছে যে third law আসলে কি স্টেট করে। So I have a couple of versions of the third law, if you remember from physics 114, যদি মনে থাকে, সেটা হচ্ছে একটা ভার্সন আছে যেটা হচ্ছে it's called Nernst version. Okay, so in that version it is stated that the third law states যে at absolute zero, say, let me write it like this. Okay, so absolute zero temperature, cannot be reached by a finite number of steps. And this was proven for black holes by Wald in 1974. যে এরকম similar একটা analogy you can get to, মানে এরকম একটা similar একটা analogy আমি বের করতে পারবো for kappa, because you understand that temperature analogy, মানে analogy আমরা যেটা বানাচ্ছি সেটা হচ্ছে for kappa, right? Surface gravity. So তার মানে absolute zero temperature এর analogous quantity should be the extremal limit where kappa goes to zero, right? So if I say, let's say temperature by absolute temperature is when T goes to zero. And if the zeroth law analogy exists, then for me, kappa going to zero is the absolute extremal, right? The absolute zero temperature analogy. So this is the extremal limit. And Wald, like I said, proved J for, okay, let me write what Wald stated particularly. J, the closer the state of the black hole is to the state of an extremal black hole, which is where আমরা দেখছি kappa goes to 0, right? Extremal black hole. The harder it is to get even closer. Meaning, try to think of it like this. Well, I don't know how to explain this, but okay. So let's say আমার extremal black hole reach করার ব্যাপারটা যে let's say আমরা কয়েকটা কিন্তু অ্যানালজি দেখছিলাম ইভেন ফর রাইজন নর্জন ব্ল্যাক হোলস যে আমাদের যখন একটা এক্সট্রিমাল লিমিট থাকে সেই এক্সট্রিমাল লিমিটের জন্য হ্যাঁ ফিজিক্যালি অ্যান্ড ম্যাথমেটিক্যাল লট অফ থিংস ইজ পসিবল বাট আমরা কিন্তু দেখছিলাম যে ইট ইজ ভেরি ডিফিকাল্ট টু রিচ দি হরাইজন ওয়েন you have the extremal limit, right? And extremal limit horizon reach kora kintu it takes infinite number of steps technically, like distance is infinite, right? So in that case, what Wald proved over here is that, let's say আমার একটা black hole state এরকম আছে যে it is really nearing towards becoming an extremal black hole, so kappa going to 0, right? Something, but let's say my surface gravity for a particular black hole is very near to 0, okay, so it is closer to being an extremal black hole. সেই ক্ষেত্রে the more your value for kappa goes to near 0, the harder it is to reach that 0. What it means is that if you think of it from the number line perspective, it's like I'm going towards 0. So if 0 is over here and kappa is over here somewhere. Okay, so kappa is equals to something. Okay. And the closer I'm going to 0, the limit, it gets harder and harder to actually reach kappa equals to 0. It's like the closer you get to 0, the whole system tries to resist you from going to 0. Okay. So it is similar to the 0th law, especially Nernst's version of the third law, sorry. যে absolute zero temperature cannot be reached by a finite number of steps. তার মানে absolute zero temperature কিন্তু reach করা খুবই tough, which is something that we experimentally see as well, right? We cannot reach absolute zero because that is a state of complete কি বলবো zero entropy, and zero entropy state reach করা is almost impossible, right? So in that case, this is also fundamental to the fact that আমাদের যে থার্ড ল করেসপন্ডেন্স আছে সেই থার্ড ল করেসপন্ডেন্স কিন্তু এই যে এন্ট্রপি করেসপন্ডেন্সের সাথেও ট্রু, যে আমি কখনো কিন্তু সিঙ্গুলারিটি মানে লেটস সে a ইকুয়ালস টু 0 ইজিলি রিচ করতে পারবো, রাইট? সো ইটস সর্ট অফ লাইক ইফ ইউ থিঙ্ক অ্যাবাউট ইট লাইক দিস, যে একটা অ্যানালজি যদি আমি বানাইতে চাই সেই ক্ষেত্রে লেটস সে ইটস লাইক well, I don't know. I don't have a certain example in mind, but it's sort of like it's harder to reach absolute zero because you think about experimental stuff. There will always be something barring you from reaching zero entropy, right? Because we understand that entropy will always increase. So কোনো একটা physical mechanism দিয়ে যদি তুমি একদম entropy কে null করতে পারো, that is very harder to reach experimentally. So essentially that is what the third law states, যে absolute zero is not attainable, and if it is, then it takes a lot of effort. Okay, so এই অ্যানালজির সাথে কিন্তু আমি হচ্ছে টেম্পারেচার অ্যানালজি করতে পারি with the surface gravity, and therefore you have a sort of relationship between the 0th law and also the third law of thermodynamics. Okay, so now key question. Yes, you have to think of experiments.
It's not a fairy tale.
হ্যাঁ, of course
You
you
need experiments.
of course you have to think of experiments.
আমি
But for
ফেরি টেল
anything
পড়তেছি।
for anything to be like justifiable, you need experiments. But the thing about physics is, especially the physics that we do, is that and a lot of these things are not experimentally viable yet. Okay, for example, you cannot bring a black hole into a lab. You cannot do that. Kintu at least আমাদের physicsটাকে তো justify করতে হবে, right? And especially if we're talking about classical thermodynamics is experimentally viable. So in that case, আমরা যদি সেই analogyটা make করতে চাই, I need to make sure that whatever I'm talking about is also experimentally viable, right? So now moving on, if we want to compare the zeroth, first, second laws of thermodynamics now with black hole mechanics, তখন হচ্ছে আমরা এই যেটা আমরা উপরে লিখছি এই যে ফার্স্ট ল এর সাথে আমরা এরকম অ্যানালগাস রিলেশনশিপস বিল্ড করতে পারবো, মানে কম্প্যারিজনে একটা করেসপন্ডেন্স বিল্ড করা। সেই ক্ষেত্রে ফ্রম দিস এক্সপ্রেশন and by comparing it with this expression, okay, I can make a particular relationship that there is a correspondence between E with mc squared, okay, which is something you've seen before. Furthermore, you can make an analogy with temperature and correspond it to this expression over here, and we can write this as alpha c square kappa by g. যেখানে এই alpha is some undetermined constant, just like establishing a proportionality, okay. And furthermore, you can make an analogy with the entropy with again this expression over here, where you can write it as 1 by 8 by alpha A. Okay. So you see, this is basically when I am comparing zeroth, first, and second laws of thermodynamics. Can I should write down that alpha is just an undetermined constant, something that is undetermined for now. Okay. Now, this is not a coincidence, obviously. মানে আমরা ধরে নিতে পারবো না যে হচ্ছে let's say আমরা কোইন্সিডেন্টালি আমরা একটা হুদাই একটা অ্যানালজি বানাই দিলাম যে হ্যাঁ E is equal to mc squared, T is equal to alpha blah blah blah, S is equal to some expression of A. You cannot make that out of thin air, right? So এখানে আইডেন্টিফিকেশনটা ইম্পর্টেন্ট যে আসলে এই রিলেশনশিপটা কোথা থেকে বিল্ড হচ্ছে। সো অফকোর্স E আর M কে এখানে যদি দেখো, E আর M কে করেসপন্ড করাটা খুবই ইজি, বিকজ মানে এটা পিওরলি জাস্ট আউট অফ থিন এর আসা নেই। আমরা জানি যে E আর M both represent sort of energy of the black hole system, right? ওটা আমরা দেখছিলাম even when we were dealing with the Penrose process as well, right? যে mass depletion একটা ব্যাপার আসে when you have energy to be negative. So in that case, we understand that both energy and mass sort of give you an idea of the total energy of the system. So in that case, this analogy makes sense, okay? On the other hand, আমরা যে আইডেন্টিফিকেশন গুলো করতেছি অন্যগুলার যে টেম্পারেচারের সাথে বা এস এর সাথে, সেগুলো একটু মানে গাঁজাখুরি টাইপের মনে হয়। সেটার কারণ হচ্ছে যে দে ডোন্ট রিয়েলি ম্যাচ ইন ডাইমেনশনস, যেটা আমি প্রথম দিকে বলছিলাম যে টেকনিক্যালি এগুলো নন ফিজিক্যালি মনে হচ্ছে, কারণ হাউ ক্যান টেম্পারেচার বি রিলেটেড টু sort of kappa, right? So in that case, it seems like it is non-physical. Now, আরেকটা জিনিস এখান থেকে আমি ডিনোট করতে পারি যে ইফ আই রিয়েলি ওয়ান্ট টু মেক আ রিলেশনশিপ বিটুইন দ্য টেম্পারেচার অ্যান্ড কাপা, আই নিড টু স্টেট আ ফিউ থিংস। একটা হচ্ছে ফার্স্টলি আই নো দ্যাট দ্য ফিজিক্যাল টেম্পারেচার অফ আ ব্ল্যাক হোল let's say in classical GR is 0, right? কারণ আমি জানি যে in classical GR black holes don't really radiate anything, right? In that case, you should not feel any temperature coming out of the black hole. So in that case, in classical GR, the physical temperature of a black hole is absolute 0. And that is solely because আমরা consider করি that the event horizon of a black hole bars it to emit anything, তাই না? তার মানে হচ্ছে black holes are actually pure absorbers. They don't emit anything, they only absorb. That is what we know is true for classical black holes in general, right? So if it is a perfect absorber, then it has absolute 0 temperature because it does not radiate anything. Now, এটার ক্ষেত্রে হচ্ছে আমরা মানে sort of বুঝতেছি না how it can really correspond to temperature and surface gravity. Now, this is one problem. Another thing I can note for the second analogy over here, actually the third, maybe I should call it the third, যে এন্ট্রপি আর এরিয়া রিলেশনশিপ কোত্থেকে আসে, হোয়াট ইজ দিস আইডেন্টিফিকেশন, রাইট? নাও দিস ইজ a little um curious in the sense যে এই রিলেশনশিপটা আসলে আমরা কিভাবে বিল্ড করছি। But this was considered to be a very formal notion in the sense যে আমরা just একটা mathematical analogy বানাচ্ছি, not anything physical, until we sort of discovered the Hawking effect, right? And Hawking effect এর idea থেকে কিন্তু we have like the Bekenstein-Hawking entropy and all of that stuff, যেখানে the Bekenstein-Hawking entropy is directly related to the area of the black hole. সো হকিং এফেক্টের আইডিয়াটা কি, যেটা আমি হচ্ছে রিমেম্বার কিফটিন কার্ভ স্পেসে বলছিলাম, যখন আমরা কিফটিন কার্ভ স্পেসের একটা ক্লাস নিয়েছিলাম, সেখানে যে when you have quantum effects around the event horizon you have the production of particles, right? Particles and antiparticles, and in that essence when you have particle production near the event horizon you can have, you know, one of the particles in the pair to be sucked in by the black hole and the other one being, you know, thrown out. That is the Hawking effect. Okay. And via that, you can then have something called the Hawking radiation, where you directly relate, you know, your temperature with the mass of the black hole and so on. So তখন কিন্তু black holes don't become, black holes are not anymore a perfect absorber. It emits radiation. Okay. And if it emits radiation from the event horizon, you can actually clearly see that there has to be a relationship between the surface gravity and the temperature. So until the discovery of the Hawking effect was made, we thought that these relationships were just purely formal, meaning যে আমরা just একটা mathematical analogy বানাচ্ছি. So এটার ক্ষেত্রে এই যে কি বলবো বেকেনস্টাইন হকিং এন্ট্রপি এন্ড অল অফ দ্যাট স্টাফ আসছে, এটার পর থেকে হচ্ছে একটা ফিজিক্যাল কানেকশন আমরা বানানোর চেষ্টা করছি, যেটা হচ্ছে মোর রিয়েল, and that generalized the second law of thermodynamics for black holes, which states, let's write it as the general second law of thermodynamics, black hole thermodynamics, which is stated as the sum of the black hole's entropy and the entropy of matter outside would never decrease. Okay, which is given by this expression, which states that this will never decrease. Okay, now we see that in fact econo, even though we have this general idea of, you know, the second law, the existence of black holes is not really compatible with the ordinary second law of thermodynamics যেটা আমরা জানি for in case of, you know, the entropy increasing. এটা সমস্যা হচ্ছে কি, if you try to analyze this, whenever we have a black hole, right, and let's say there is matter outside the black hole, সেক্ষেত্রে if I'm an external observer over here, in that case আমি হচ্ছে এখানে একটা entropy calculate করতে পারবো for anything that is outside the black hole, right? But now let's say things are sucked in the black hole. Okay, in that case it disappears completely, right? এটা পুরাটাই event horizon এর ভিতরে চলে যাচ্ছে। তো সেই ক্ষেত্রে ফর দি এক্সটার্নাল অবজারভার আমার কাছে মনে হবে যে এন্ট্রপি আসলে ডিক্রিজ করতেছে, বিকজ I would be counting lesser microstates, right, in that notion. So if I have lesser microstates, I would see that the entropy actually decreases. So therefore the very existence of black holes and the idea of this assimilation of, you know, matter that gets sucked in into the black hole directly contradicts with the second law of thermodynamics. Because how can entropy decrease, right? However, I also know that the area of the event horizon actually increases, right? So তার মানে এখানে দুইটা নোশন আছে, একটা হচ্ছে যে এক্সটার্নাল অবজার্ভারের জন্য Classical second law of thermodynamics actually break করে if there is an existence of the black hole. But through assimilation, তার মানে হচ্ছে when particles go in, I have the area of the event horizon to increase. So তার মানে simultaneously দুইটা জিনিস হচ্ছে। একটা হচ্ছে যে একটা এক্সটার্নাল অবজার্ভার ম্যাপ করবে যে এন্ট্রপি ডিক্রিজ করতেছে, রাইট? সো ডেল্টা এস decreases. However, of course, that is not possible, right? বাট অলসো এটা আমি খেয়াল করবো যে একটা এক্সটার্নাল অবজার্ভার দেখবে যে যখন অ্যাসিমিলেশন হচ্ছে, তার মানে যখন পার্টিকলস গুলো ঢুকতেছে ভিতরে, the area of the event horizon increases. So তার মানে there must be a relationship between these two, right? যে আমি যখন দেখতেছি যে একটা সিস্টেমের এন্ট্রপি ডিক্রিজ করতেছে and it is being covered up by another system's area increasing, that must be there must be a relationship between the two, and that is what happens in general, right? যে আমরা যখন একটা thermodynamic system নেই, let's say you have a thermal bath and you have let's say a system, হ্যাঁ, and with দুইটা সিস্টেমের মাঝখানে there is thermal contact, so there that means that there is, you know, sort of interaction between the two. So in that case, if the system's entropy increases, then of course, you know, আরেকটা সিস্টেমের যে thermal bath or whatever is it connected to it, entropy decrease করে. We understand that this happens in general in thermodynamics, right? So সেই ক্ষেত্রে এই সিস্টেমটাকে যদি আমি একটা isolated system হিসেবে চিন্তা করি, where you have, you know, the universe inside a box, overall this change in entropy, or in fact the fact that এখানে delta S goes to 0 makes sense because it is now covered with the, you know, increase of entropy, sorry, increase of area, which technically now you can relate to the entropy. Okay. So this is true because somebody, and I think this somebody is Bekenstein, suggested that the generalized entropy which is given as S prime is defined as S plus A by 8 pi alpha does not decrease. And you see why, right? Because if I have an assimilation, আমি যেটা বললাম, সেটা ক্ষেত্রে ধরলাম আমার আউটসাইড বাসের এন্ট্রপি ডিক্রিজ করলো, but that is covered up by an increase of area, right? So in that case, যদি generalized entropy আমি consider করি as a combination of this entropy and the area, S prime really does not decrease, right? So it is true to the second law of thermodynamics. So that's fine. So now আমরা যেটা করবো সেটা হচ্ছে we're going to try and sort of, you know, make this analogy more concrete by doing a little bit of dimensional analysis. So in this case, we're going to consider the fact that এখানে যে অ্যালফাটা আছে, যেগুলো সব অ্যানালজি গুলোকে স্কেল করতেছে, ফর এক্সাম্পল this one and this one too, এই অ্যালফা যেটা একটা আনডিটারমাইন্ড কনস্ট্যান্ট, সেই ক্ষেত্রে অফকোর্স দিস অ্যালফা উইল বি preceding in our notion of dimensions if we want to really make a relationship between the two, right? So we can consider that, for example, if the entropy S has a dimension of, I know, the Boltzmann constant, right? So if S has dimensions of KB, the Boltzmann constant, in that case, if I want to make a relationship between these two, আমি এটা এখানে লিখে রাখি for reference so that I can relate it to 8 pi by alpha, right? So if this has dimensions of KB, then alpha must have dimensions of what? So alpha must have dimensions of length squared, right? Sorry, alpha KB must have dimensions of length squared. Because if alpha KB has dimensions of length squared, then you can relate the two, right? So this will be KB, and this will be, you know, some length square, which will length square, and you will have KB, and this will, you know, basically diminish that length, and overall dimensional analysis will give you KB. Okay, so এখানে একটা প্রবলেম হচ্ছে যে এই যে লেংথ স্কোয়ার আমি যে বানাবো বা অ্যালফা কেবিকে যে আমি বলবো যে it has some dimensions of length squared. In that case, what is this length that I'm considering over here? আমার কোনো এরকম generalized length বের করতে হবে যেটা is actually denoting this alpha kb dimensions, right? So what we can do is we can sort of consider all the physical constants that we have in GR in general. সেটা হচ্ছে, you know, G, C, and H bar, right? In that case, একটা জিনিস এখানে is viable. সেটা হচ্ছে যে if we want to denote this length squared, we can consider physical constants from GR, which is going to give us Newton's constant G and speed of light C, right? But আরেকটা জিনিস আমি এখানে নোট করতে চাই, সেটা হচ্ছে যে the reason why we can actually relate S and A is because of quantum effects, right? If you remember, the reason why we can actually do this is because of Hawking effect, right? তো হকিং এফেক্ট ইজ আ কোয়ান্টাম এফেক্ট, এন্ড কোয়ান্টাম এফেক্টের কারণে কিন্তু আমাদের এই অ্যানালজি গুলো পসিবল হয় ফিজিক্যালি। সো সেক্ষেত্রে why not use physical constants also from quantum mechanics, which is h bar. Okay, and these are all your, you know, components of natural units as we know, right? So in that case, we have a fundamental length which we can form using gc and h bar, which is the Planck length, which is given as lp. And it is formulated via this expression. I'm pretty sure you've seen this before. Okay, I mean, this is something I don't know if you've done this, but this is something that we start with when we do classical mechanics. Okay, or mechanics in general, I think. So with this fundamental length now, we can sort of make the analogy that KB alpha should be proportional to, like I said, some length squared, and therefore this fundamental length is the Planck length. And hence, you can use this and go further in the analogy and write that the temperature is now proportional to h bar k kappa, kb c, and s, which is the entropy, proportional to c cubed a gh bar. Okay. So now, basically, what I'm trying to say is that now you can sort of make a physical relationship, a physical analogy between black holes and thermodynamics if you consider this proportionality. Now they are dimensionally all right, number one. Number two হচ্ছে যে this has been possible only if you consider quantum effects. Okay, because quantum effects gives you the idea that, you know, the surface gravity can be directly related to the temperature. And also using quantum constants like the h bar, you can figure out that this relationship of alpha, which is the proportionality, is, you know, therefore viable in terms of, you know, sort of actually stating that these are equivalent quantities. Okay. Now, to end, I would like to state another thing that I'm already state করছি, সেটা হচ্ছে যে these black hole laws are not actually laws per se, because like I said, you cannot really experimentally verify them to be universal. However, we understand the thermodynamic laws, যেগুলো classical thermodynamic laws, they are universal because they are, you know, testament to all conditions in every condition. So সেই ক্ষেত্রে হচ্ছে এই ব্ল্যাক হোল লস দেরকে টেকনিক্যালি আমরা থিওরামস বলবো, because these are within the theory of GR, because GR predicts these. So in that case, I would say that these theorems, যেটা হচ্ছে ব্ল্যাক হোল থার্মোডাইনামিক্স কে গভর্ন করে, এই থিওরাম গুলো কিন্তু is applicable to general black holes, in the sense that if you have the no-hair theorem, any black hole that you can construct using the no-hair theorem, you can generalize these laws or theorems per se for those black holes. So this is true for, you know, all black holes that can be generalized. Okay. নাও আরেকটা জিনিস আমি স্টেট করতে চাই ফাইনালি, সেটা হচ্ছে যে আম, এই বেসিক্যালি এই আন্ডারস্ট্যান্ডিংটা আমাদের, যে থিওরেমের আন্ডারস্ট্যান্ডিং বা এই যে ইউনিভার্সাল বিহেভিয়ার অফ ব্ল্যাক হোলস, যেটা আমি বলতেছি যে অল জেনারেল বা ইউনিভার্সাল ব্ল্যাক হোলস উইল অ্যাবাইড বাই দিস থার্মোডাইনামিক theorems of black holes, এটা is more testament when we, again repeating myself, consider quantum effects. So therefore it is very interesting, and in fact something that we would like to further study is how this quantum nature of black holes actually form. Okay, because all we've done so far in this whole course is we've studied classical nature of black holes, which is testament to GR, right? Because GR is a classical theory. So GR এর একটা সুন্দর application হচ্ছে black holes, but this is a purely classical theory. However, we see that, when we are relating thermodynamics, which is, something that is very solid in nature, like thermodynamic laws have never been broken. Energy conservation is broken in the universe, we know that, but the second law of thermodynamics is universal, it is never broken, right? So thermodynamic laws are very like solid. তো আমরা যখন এরকম একটা সলিড একটা সেট অফ লস কে ব্ল্যাক হোলের সাথে রিলেট করতে চাচ্ছি বা অ্যানালগাস করতে চাচ্ছি, তখন আমরা দেখতেছি যে ব্ল্যাক হোলের কোয়ান্টাম এফেক্টস গুলো আরো অ্যাপারেন্ট হচ্ছে, যে উই নিড কোয়ান্টাম এফেক্টস টু অ্যাকচুয়ালি মেক দিস রিলেশনশিপ পসিবল। তো সেই ক্ষেত্রে ইটস এ ভেরি ইন্টারেস্টিং থিং টু work on quantum black holes, which is something that I am particularly interested in, right? Because not only does these quantum effects give you more idea about black hole thermodynamics and what you can do and study about them, it also tells you a lot about quantum gravity as well, right? How if black holes are the test of gravity, like these are the gravitational stuff, right? In that case, if you can quantize these black holes or at least understand their quantum nature, it should give you a very big window to look into quantum gravity. So in that case, it's more comprehensible if we study quantum black holes. And if I ever get a chance to maybe, make another course, maybe I would like to do it on quantum cosmology or quantum black holes in particular. So it would be an interesting topic of discussion. So essentially, end notes is the black hole thermodynamics is pretty cool. And in order to study them further, you need quantum effects. And yeah, that's it. And that is it for the course. And
Was the pun intended?
keep on kunta.
Black hole thermodynamics is pretty cool.
Oh, it's a nuts. But yeah, okay. So yeah, that is for the course. We've studied only classical stuff. It would be nice if we could extend it to other stuff, but we don't have the time to do that. But I feel like we've covered enough for an undergraduate course on black holes. So we've covered everything starting from Schwarzschild. Actually, we started from gravitational collapse, the Oppenheimer standard model. And then we went to Schwarzschild black holes, which are just generic black holes with mass, with no spin, no charge. And then we moved on to charged black holes, trisonorsum black holes. We constructed their, ambiguous physics, which was pretty interesting to study and also teach. And then we went to black holes with angular momentum, curved black holes. And then finally relating all black hole properties to thermodynamics. And therefore ending it with a note that quantum effects are important to study and understand black holes better. Okay, so that's it for today. If you guys have any questions, you can ask me. And Rafsan, you wanted to sit afterwards with the paper. Let's do this. সেটা হচ্ছে যে স্যাটারডেতে আমি ব্র্যাকে আসবো, আমি এটা সবাইকেই বলছি যে স্যাটারডেতে I'll be available at BRAC, I think from 11 to 1. Or maybe I can come earlier. Let's see. But 11 to 1 I'll be there. So come then.
Okay.
ততদিন পর্যন্ত তুমি just accumulate করো যা যা problems আছে, questions আছে. And Saturday we'll sit with everyone's problems on the paper. Okay?
Okay.
Acha. So I'll stop the recording.